Let's do a brief recap on what we learned in the previous class. We have seen that a laser can be pictured as a medium in which population has been inverted between two energy levels. The ground or the lower level and an excited energy level that we call E2, and the lower or the ground level we call E1. And this population inverted medium, that is a medium in which gain has been established, is placed inside a cavity. One of the mirror of the cavity, as we know, is 100% reflective, while the other mirror is partially transitive, through which the laser beam is coupled out as a useful loss, and it makes the output of the laser. However, as we know that an excited species can only spend a finite amount of time in the excited state, the energy level as a consequence of Heisenberg uncertainty principle is actually broadened. And therefore, the gain that has been created between these two energy levels do not occur at a single frequency. Instead, it would be spread on numerous frequencies. That is because the gain does not occur only on the frequency which we call line center frequency, which basically, if nu 0 is the line center frequency, then h nu 0 will be equal to E2 minus E1, or in other words, nu 0 will be equal to E2 minus E1 by h. However, there would be a transition from this point to the lower energy level, whose frequency will be less than this, and the transition from this point to the lower energy level will have a frequency which will be more than this. And the transitions which originate from intermediate points will have frequencies ranging from lying between these two frequencies. And therefore, the gain, if this is our line center frequency nu 0, here the gain of course will peak, but it will drop off on either side. Now, the gain thus occurs at numerous frequencies, and now when we place this gain medium inside the cavity, there will be spontaneous emission on all these frequencies, which will oscillate back and forth inside the cavity. So, obvious question that can be asked here is, can the laser laze on all these frequencies for which there is gain? The answer is an emphatic no. Lasing would occur only on those frequencies which are cavity modes, which can oscillate back and forth inside the cavity without decaying. Now, all these discrete frequencies I show here are actually cavity modes. The spacing between two cavity modes, adjacent cavity modes, as you know, is inversely proportional to the cavity length L. C is of course the velocity of light. Now, of course, there are many such cavity modes ranging from low frequency to high frequency. I show only those few modes which overlaps with the region of gain. Now, all these modes, you see, have gain, small or big. Does it mean that lasing would occur on all these cavity modes, which can oscillate back and forth inside the cavity? The answer is once again a big no. In order to understand this, let us go a little deeper. You see, in a typical laser, one of the mirrors of the cavity is actually 100% reflective, meaning no light can leak through this mirror, while a small transmission loss is provided to the other mirror, through which the light that stores inside the cavity is part of it, is coupled out as a useful loss that forms the laser beam. Now, this transmission loss is independent of the cavity mode frequency. They are same for all the cavity mode frequencies. If we assume that, then the loss can be represented as a straight line in this gain curve. Let us assume that this is the loss line. This is the loss line. And this is gain. Now, lasing would be possible only on those modes which have net gain, meaning whose gain exceeds loss. Now you see, in this particular example, you see this mode has a gain this much, while it has a loss which is just this much. That means this mode has a net gain, therefore it will be able to less. Now if we consider this mode, this has a gain which is this much and loss which is this much. Therefore this mode has a loss that exceeds gain. Therefore this cannot less. It will die out on its own. It cannot grow. In this example, therefore, you can say that there are only 1, 2, 3 modes for which the gain exceeds loss, and therefore lasing will be affected on all these 3 modes, and the emission feature of the laser would look somewhat like this. If we draw power versus the frequency of the laser, then lasing would be in all these 3 modes, and the mode with higher gain also will give out higher power. So this would be essentially a multi-mode laser, and you can appreciate the fact that the emission feature of the laser, the emission of the laser is not highly monochromatic because the emission frequency ranges over a large region, because it is a multi-mode laser. Although the emission is much more monochromatic compared to a conventional source, yet the monochromaticity of the laser, of this multi-mode laser, is not very great. The monochromaticity can be greatly improved by restricting the number of oscillating modes. This can be achieved in a number of ways. For example, if we reduce the broadening of the gain, so much so that this is the gain and this is the loss. This is the loss line, this is the gain. We have reduced the broadening of the gain so much so that now you see only this mode has a net gain. This is the loss and this is the gain. No other mode now has a net gain. For example, this mode has this much loss and this is this much gain and this is loss, which exceeds the gain. Therefore, lasing will now be essentially affected only on this mode, which has alone net gain, and therefore it would be basically a single mode laser with greatly improved monochromaticity. The same also can be achieved simply by reducing the cavity length. For example, we bring the cavity mirrors closer. So if we bring the cavity mirrors closer, the free spectral region, that is the spacing between 2 adjacent cavity modes, which is inversely proportional to the cavity length, will move away from each other, and therefore once again providing a situation wherein only this is our original gain was this, and this was the loss line. Now you see the modes are so widely spaced that there is only Thus, you see, reducing the cavity length, that is bringing the mirrors closer to each other, once again closer to each other, pushes the modes away from each other, thereby presenting once again a condition where is only one cavity mode. Here, this mode alone has a gain which exceeds loss. No other mode will now have a net gain, therefore, lasing would once again be affected on a single mode. However, in both these techniques, the single mode or the monochromaticity of the laser has been attained at a price, basically at the expense of the operating performance of the laser. Because you see, in the first case, we reduce the broadening of the gain. And the broadening of the gain, to achieve this, for example, say our laser is a gas laser. This reduction of the broadening of the gain is possible by reducing the operating pressure of the laser. If you reduce the gas pressure, then the constituent atoms of the gas will collide with less frequently. Therefore, the chance that this collision will relax the excited atom in the ground state will be less, because they will collide less frequently, and therefore this will result in increased lifetime of the excited level. And increased lifetime means, according to Heisenberg's uncertainty principle, if you increase the lifetime, then the broadening of the energy level accordingly reduces. And so gain broadening reduces when we reduce the operating pressure, for in case of a gas laser, say. Now, reduction of pressure basically reduces the density of the active atoms in the discharge chamber. So if the active atom reduces, that means we have got monochromaticity at the expense of the output power of the laser, because this active atoms alone produces the laser photons. In the second case, we obtained monochromaticity by reducing the cavity length. That means we brought the cavity mirrors closer to each other. Now, to accommodate the active length, we have to basically reduce the active length of the laser. And reduction of the active length would once again cause reduction of the output power of the laser. Thus, in both these techniques, monochromaticity has been attained at the expense of the operating performance of the laser. The same can also be achieved simply by making use of a dispersive cavity, such as a prism. As a dispersive element you can put a dispersive element inside the cavity. For example, a prism. A prism, you see, actually splits the constituent wavelength spatially. You know that a prism, if a white light shines on a prism, then the prism actually splits the light into its constituent wavelengths spatially. Therefore, in this case, the modes, there may be number of modes, which when fall on this prism, the prism splits the mode. Modes are of different wavelength spatially, thereby allowing at a time only one of the cavity mode, in this case this mode, to fall normally on the mirror. Therefore, this mode alone would be able to oscillate back and forth inside the cavity and would be able to laze by extracting energy that is continuously being pumped in the active medium towards maintaining population inversion. Other modes which fall obliquely on the output mirror would simply get lost. It will fly out, and there won't be any chance for these modes to extract energy from the gain medium. Therefore, in this case, the monochromaticity, that is a single mode emission, has not been attained at the expense of the operating performance of the laser. Another advantage of this is that you can tune the wavelength of the laser. You see, if you tune this mirror, for example, if you tune it this way through an appropriate angle, then this mode now will actually fall normally on this mirror, and therefore would be able to oscillate back and forth, and therefore lasing now would occur on this mode. The remaining modes will fall obliquely on this mirror and would simply get lost. Thus, this provides a way, not only a rotation of this output mirror, even rotation of the prism also will give you the same result. Thus, you see, you can even tune the single mode output of the laser in a very convenient manner. Thus, you see, the integration of a cavity with stimulated emission not only allows multi-pass oscillation because it just oscillates back and forth, and the exploits stimulated emission, and this light intensity grows inside, but also makes the emission of the laser directional and also adds monochromaticity to its emission. Thus, we have now zeroed in on two most important characteristics of laser, namely its monochromaticity and directionality, which in turn lead to many other attributes that a laser is associated with. However, the very first laser that Meyman operated in 1960 did not make use of the cavity. You may be wondering as to what trick that Meyman played that allowed him complete dispensation of a cavity. Well, let me digress here a little to tell you the story that goes behind the first experimental demonstration of amplification of light by stimulated emission of radiation. Those of you who would like to know the story of the invention of laser in the same word as of the inventor itself, they can actually refer to a book called Laser Odyssey, written by Meyman himself, where he has narrated all the interesting anecdotes involving the invention of laser. You see, the paper that Meyman wrote to report the invention of laser consisted of just only one illustration and an extremely small text. It seemed that Meyman did the experiment in the morning, wrote the paper in the afternoon, and dashed it off to the editorial office of Physical Review later, which is the most prestigious journal in physical science, before the end of the day. Such an urgency stemmed from the fact that at that point of time, many laboratories in the world, researchers in the world, were working hard towards achieving the first experimental demonstration of amplification of light by stimulated emission of radiation. However, the editor of Physical Review later was not impressed. He felt the data presented by Meyman in his experiment was too scanty to warrant publication in a journal of the repute of Physical Review later. Therefore, he took a unilateral decision and rejected the paper. The paper then crossed Atlantic and reached the editorial office of Nature located in London. The editor here acted wisely and got the paper published very promptly. That has since been regarded as the first ever experimental demonstration of amplification of light by stimulated emission of radiation. Well, let's see, returning back to science, let us see as to what was the signature of amplification of light by stimulated emission of radiation in his experiment that convinced Meyman to believe that indeed he had operated the first ever laser. You see, the experiment that Meyman did was extremely simple. He used a cylindrical ruby rod and optically pumped it by deriving light from a flash lamp. I'll come to the optical pumping and flash lamp in a while, but the experimental system that Meyman used, I have shown here. This is a schematic representation of the experimental arrangement Meyman used to create the very first laser. The flash lamp was in the shape of a helical, it had a helical geometry, and Neyman placed the ruby rod at the center of the helix, and the flash lamp emits light and it would shine the ruby from all sides. Now you see, flash lamp actually works almost the same way as a fluorescent light that you have already studied. It has a discharge tube, and at two ends of the tubes you have two electrodes. And as you apply voltage to the electrode, of course, you have taken a gas in the flash lamp in such a way that the gas, that constituent of the gas, emits a light which is absorbed by the ruby molecules in the ruby rod. So you have carefully, appropriately chosen the wavelength of the light that this flash lamp emits. Now, it's just there are stray electrons present in the discharge tube. When you apply the voltage, the stray electrons in particular will be accelerated and gain kinetic energy, collide with other neutral atoms present in the flash lamp. They will be ionized, more electrons will be created, and so a current will flow through the flash lamp, and many of the collisions that the electrons will have with the neutral atomic species will transfer part of the kinetic energy and excite the atoms electrically, and therefore the atoms comes down to the ground state and emits the excitation energy as spontaneously as photons, and this spontaneous emission basically forms the emission of this flash lamp, and this light actually shines, the geometry is such that it shines the ruby rod from all sides. Now, ruby rod will be molecules in the ruby rod will be excited by these photons emitted by the flash lamp, and therefore the ruby, after excitation, ruby molecules will come down to the ground state, and as it comes down, it will again fluoresce light, and this fluorescence has a spectral weight for the same reason for which gain has a spectral broadening, the Heisenberg uncertainty principle, because the excited ruby level is actually broadened in energy, and therefore there will be a number of emissions from the ruby excited energy level to the ground level, resulting in that observed fluorescence, observed broadening of the fluorescence. Neyman basically wanted to study this fluorescence as a function of the wavelength. He placed a detector on one end of the ruby rod, and basically he studied three cases. In the first case, he pumped his ruby rod very softly, means the intensity of the light emitted by the flash lamp was pretty low. This was possible by using a low, operating the flash lamp at a low voltage. Lower voltage, the four electrons will acquire less energy, and therefore less number of ruby molecules. Sorry, flash lamp, the constituent species of the flash lamp will be excited, and this will result in emission of less number of photons, which will pump the ruby rod. In this case, when he pumped it very softly, Neyman observed that the spectral width of the fluorescence matched the known fluorescence with spectral width of ruby. It was absolutely fine. In the second case, Neyman increased his intensity of pumping, but still not good enough to create population inversion along the ruby. To increase the intensity of pumping, he had accordingly increased the voltage that was applied to the flash lamp. In this case, because he pumped it with light of higher intensity, that means more number of ruby molecules are excited. Therefore, the intensity of the fluorescence of ruby also, in accordance with increased intensity of pumping, rose. As you can see here, the intensity of fluorescence is more. However, the spectral width of the fluorescence remained invariant. It was just same as before. In the third case, Meyman pumped his ruby very hard by making the flash lamp produce much more photon within a given area. And the pumping was so hard that in this case, population inversion was created along the length of the ruby rod. And in this case, Meyman found a significant narrowing of the spectral width of the fluorescence as the probability of stimulated emission at a given frequency increases with increasing presence of photons at that frequency. Meyman knew for sure that this spectral narrowing of the fluorescence is indeed a signature of amplification of light by stimulated emission of radiation. I will provide you now a physical insight which will say why spectral narrowing will provide a signature of lasing, that is a signature of amplification of light by stimulated emission of radiation. For this, let us divide the ruby rod into small sections, number of small sections. Now, we have created population inversion. Now, let us first assume the small section. Ruby molecules have been excited, therefore, they will come down eventually to the ground state and emit this excitation energy as spontaneously emitted photon, and these photons will have a spectral distribution as we just explained, and also they will be emitted in all possible directions. Out of that, a small fraction of the photons which will be emitted along the axis of the ruby rod, that will appear now in this section. So first you have a spectral width of that emission. This distribution of photons will now appear in the second section. Now you see at this frequency, this is the frequency, this is the intensity of fluorescence. Now at this frequency, the intensity is maximum. That is, maximum number of photons are presented at this frequency. Now when this distribution of photons comes here, they will now stimulate, because there is gain here. You have inverted population. They will now stimulate, they will now do stimulation of the excited molecules in this region. Now stimulation will be more at this frequency when number of photon is more. Wherever the photon is more stimulation will occur. Then at the wings, where the number of photon is less, intensity is more, means number of photons are more. Therefore, the distribution that will the photon distribution here, more amplification will be occur at this wavelength, at this frequency, and less will be at the wings. Therefore, there will be a narrowing of the fluorescence width. Now, this is what is actually happening, and if you see the net result as they move progressively through these sections, what happens? This initial distribution actually slowly gets and progressively gets narrowed and narrowed and narrowed, and eventually it gets spectrally significantly narrowed. Thus, I think I have made it amply clear to you as to why spectral narrowing indeed provided a signature of amplification of light, and Meyman used this as an evidence that he had operated the first ever laser, although he never operated his laser based on the concept of a cavity. Now you see, the integration of cavity with stimulated emission has given laser almost all its attributes like monochromaticity, coherence, tunability, directionality, brightness. A laser can also be operated both in continuous and in pulsed mode. In the pulsed mode of operation, suppose this is your laser, you are pumping it continuously, and the output of the laser, if we plot the laser output, output power. In time, it will produce a continuous power in time, continuous operation. A laser can also be operated in pulse mode where the energy is dumped into the laser load within a small time, and therefore the laser actually would produce a pulse instead of providing a constant power output. In the pulsed operation, evidently or essentially, the peak power of the laser can be much higher than the CW power. And if you pulse it repetitively, then the laser will produce pulses also in the repetitive fashion. So although the peak power can be increased, however, the average power of this repetitive laser, however, may remain just the same as in case of continuous operation. With judicious manipulation of some of the operating parameters of the laser, it can be also made to produce a giant power into which a huge amount of energy would be confined within a small time. This is the time, this is the intensity. This would produce enormously high intensity that can do simply wonder. By intelligent manipulation of some other operating parameters of the laser, a laser can also be made to emit ultra short pulses, which can go down to the regime of femtosecond and even beyond. All all these, however, beyond the scope of this course. Now, these unique features of laser have resulted in widely varying applications in diverse areas such as medicine, manufacturing industry, nuclear industry, communication, defense, science and education, conservation of artwork, entertainment, holography, advancement of science, almost anything that you can think of this. There is hardly any discipline left today where lasers have not made a cut. However, a single laser cannot be applied everywhere. One needs different lasers for different applications. Today, there exists innumerable number of lasers providing coherent light, spanning across infrared, visible, ultraviolet, and even vacuum ultraviolet region of the electromagnetic spectrum, and even beyond. It is important to know the working of some of the important lasers that have made significant impact on humanity. I shall try to explain the operation of some of them in as much simple manner as possible as we advance into this course.